in the last lecture, we had developed 3 two-dimensional crystal systems and along with 3 two-dimensional conventional or two-dimensional conventional unit cells, in which we had made use of the point symmetries 1, 2, 3, 4 and 6. Now, and the mirror symmetry is still not used. So, let us continue from where we left off in the last lecture and add now a mirror symmetry to the vector A. So, this is, I will say, reflection symmetry is added. So, I have the vector A and perpendicular to this vector is a mirror denoted by M. Now, where can I put the second vector B in this case? Because this mirror, if I do a reflection of this mirror, then this vector A will be pointing in the opposite direction. So, does that mean that I can put the vector B anywhere I like? Let us try it. So, let us put this vector B at some arbitrary orientation. Now, this mirror will necessarily reflect the vector B into a different orientation given by B prime. Now, imagine that I have lattice points at the end of these vectors. So, if I look at the lattice spacing along A, it is some spacing. So, this is between, let us say, the lattice points 1 and 2, it will have some spacing A. And what is the spacing between 3 and 4? Because these two lattice points 3 and 4 will also be in the same direction as lattice points 1 and 2. Now, since the vector B is arbitrary, the spacing between 3 and 4 is also arbitrary, and therefore, the lattice translation condition is not satisfied, and therefore, this will not be a lattice. So, one way to overcome this problem is to not put this vector in an arbitrary orientation, but put the vector B in the mirror itself. Now, there is no condition that is invalid in this case, and therefore, my unit cell can be defined in the form of a rectangle with lattice points at the corners and with, let us say, this is vector B. So, I can call this as a rectangular lattice type or crystal system, and I put the lattice points at the corners of the cell, then this gives me a primitive rectangle unit cell or a primitive rectangular unit cell, whichever way you want to call it. So, if I go further, for this particular cell, A not necessarily equal to B and alpha equals 90 degrees. Now, let us take an alternative configuration of the mirror. So, what can be an alternative configuration? So, let us start with the vector A, and let us say that my mirror, or let me change the orientation of the vector A. So, vector A is like this and mirror I am keeping it horizontal. So, this is the alternative configuration. Now, what will happen? How will this reflection operation operate on the vector A? Well, it will reflect the vector A on the other side, forming the vector B. Now, if I just want to create the unit cell out of this, I essentially get a rhombus and I can put the unit lattice points, creating a primitive unit cell, and this is shaped like a rhombus. So, what unit cell or what crystal system should I call this? So, this will take a little bit more analysis. Let us graphically show in a separate diagram. This is my unit cell, the diamond shaped unit cell or rhombus, in which a rhombus has all the sides which are equal, and let us draw a few more adjacent unit cells. Now, let us see what we can make out of this. I will put the lattice points everywhere, the corners of all the rhombuses that I have drawn. Now, let me draw the unit cell, an alternative unit cell. The alternative unit cell can be like this. Now, what has happened here? Now, the lattice points are at the corners of this alternate cell, and there is one lattice point in the center, and the shape is that of a rectangle. At the same time, there is a mirror out here, and this vector A, this out here is vector B, this angle is alpha, which is 90 degrees. So, I have a unit cell where A not necessarily equal to B, and the two vectors are orthogonal to each other. So, I would call this unit cell, or the crystal system for this is again rectangular crystal system. And one of the unit cells that I can draw is essentially, I will call that as a centered rectangular unit cell. So, this is not a primitive cell. If you look at this cell, there is one lattice point coming from the corners and one in the center, and therefore, this gives us two lattice points per unit cell. So, even though I have a rhombus, but rhombus, remember there are constraints on the rhombus, and what are the constraints in the rhombus? That A is equal to B, but angle could be anything. Here the constraints are that angle for this rectangle unit cell, the angle has to be 90 degrees, while there are no constraints on A and B, but there is at least one constraint in either case. So, the system we will call that is a rectangular crystal system, but centered, and the unit cell that is conventional is centered rectangular unit cell. So, both of these unit cells come under the rectangular system, just like in the Bravais lattice. Under the cubic crystal system, you get simple cubic, body centered cubic, and face centered cubic. Here you get two possibilities of conventional unit cells, and in both cases, whether it is centered or primitive, the essential defining symmetry for a rectangular crystal system is the presence of a reflection symmetry. So, what are the, if I put down what is the conclusion finally regarding the two dimensional lattices? So, conclusion is I have four crystal systems named as oblique, rectangular, square, and hexagonal. And from these four, we get essentially 5 two-dimensional lattices, and the conventional unit cells are primitive, oblique, primitive, rectangular, primitive, square, primitive, hexagonal, and so far 4. Plus, I should add the second unit cell under the rectangular system as centered rectangular. So, these are all the 5 lattices that we have in 2 dimensions. In 3 dimensions, as you know, there are 14 lattices with 7 crystal systems. Here, 2 dimensions, we have only 4 crystal systems. Now, I will just briefly talk about something regarding the symmetry of lattice and the symmetry of crystals. Let us take one of the 2-dimensional lattices. Let us take the primitive rectangular lattice. So, I have now this lattice itself can be defined by a primitive rectangular cell with the lattice points at the corners. Now, where are the symmetry elements in this, in the lattice? So, the symmetry elements in the lattice, let us look at, there has to be mirror because that was the basis for this rectangular lattice. So, these are our mirrors. And there are mirrors in the middle as well. So, these are all mirrors, and I have mirrors going through this column of lattice points and in between as well. So, these are my mirrors. Now, we can just, what we can do is we can essentially focus on the unit cell, because the unit cell then when repeated anyway creates everything in the lattice points as well as the symmetries that are present. So, I will just kind of do this. These are my lattice points at the corners of the unit cell. So, this has, and does it have any more symmetry? Yes, it does. It also has twofold rotational symmetry. At all the lattice points, as well as in the centers of the edge of the unit cell, and also in the center of the unit cell itself. So, I have a lot of two-fold rotational symmetries, and this way you can actually draw at other locations as well. So, I have out here and so on. I am not drawing everything here. So, but you can draw at every lattice point, and then in between the lattice point, and then inside the center of the unit cell as well. So, if I consider this for example, so I have out here as a lattice point, out here is a lattice point, out here is a lattice point, and then in the centers as well, like that. Now, let us take a motif and add to this lattice. So, what I will do first is I will redraw this lattice. And select the unit cell, and let me add now a motif of the kind which has only reflection symmetry. So, I can draw a so, these are two asymmetric motifs with a mirror plane in between. So, the right handed object is getting reflected on the left handed object. The combined asymmetric motif with the two asymmetric motif, it has a symmetry of reflection. Now, I add this motif to every lattice point, the combined motif. So, what I will get, this lattice point I add, the translations would take both of them to every lattice point. And you can actually put them elsewhere also, just to show . So, I form a pattern. Now, let us look at what are the symmetries in this pattern. Well, do I have horizontal mirrors as was the case in the lattice? You will notice there is no horizontal mirror. So, all of these horizontal mirrors are gone. Do I have any vertical mirrors? I do have. So, let me draw those vertical mirrors. So, I have vertical mirrors going through the lattice points. I have vertical mirror going through the middle of two columns of lattice points. So, I have vertical mirror here, I have vertical mirror here, I have vertical mirror here, I have vertical mirror here. So, you can see that, for instance, this object is getting reflected out here like that, and for that matter this mirror is reflecting both of these objects from one lattice point to the next lattice point. So, I have vertical mirrors, horizontal mirrors are gone. So, you can say that in the final this thing, no horizontal mirror. Is there anything missing? How about the two-fold rotational symmetries that were there in the lattice? So, two-fold rotational symmetry, if I try to do this, again I find that all the two-fold rotational symmetries are also gone. So, no twofold. So, no horizontal mirrors, no twofold, only the vertical mirrors are present. So, what does this tell us about the symmetry of lattice and the symmetry of crystal? Well, the symmetry of lattice is always the highest. Another way of saying is that for a given crystal system, it will have that minimum symmetry as well as some additional symmetries, and it will always have the maximum possible symmetry that can be present in that particular crystal system in the case of pure lattice. But once I add motif to it, so we can say that in general, crystal symmetry would be less than or equal to lattice symmetry. So, this is an important point to understand, but at the same time, the crystal, for example, the pattern that we have made here, it could have been atoms for that matter. So, the pattern that I have made here, it has that minimum symmetry required to be called as a rectangular system. Therefore, this is still called a rectangular system because it has one reflection symmetry, which is the vertical mirrors. So, therefore, this is still called rectangular. So, still called rectangular, and this is why it is still called rectangular, because that is the minimum symmetry required for the rectangular crystal system. So, this is an important point. This will come up again and again later on in the course. So, keep this in mind, and with this I will close the lecture. In the next lecture, I will be discussing what are called as point groups and space groups, and essentially also I will discuss a bit about what are groups. With this I conclude, and thank you.